All right, what I'd like to do in this video is I'd like to talk about statements, axioms, theorems, proofs, types of proofs, all right, reasoning, and this is really the guts of geometry. So we certainly want to learn a lot of facts about different shapes, different objects in space, and that's going to help you on the SAT, and that's all well and good. But this is also an opportunity to learn about reasoning, learning about organizing all those facts to make it easier for you to remember them, to make even less things for you to remember. Okay? And so in order to get going, I'm going to have to first give you some basics in the area of logic. So let's go ahead and do that right now. First of all, let's clear up what do we mean when we talk about a statement. Okay, so a statement is a sentence that, it communicates a fact. Let's go there. Okay, and all right, so it says some fact, and that's the definition, and it can be true or false. So we're already talking about the truth value, whether it's true or false, regarding statements. So statements can be either true or false. So let me give you some examples of statements. Okay, so the sky is blue, the moon is made of cheese, I am 90 feet tall, and you are a student. All right, so these state facts. All right, not all of them are true, not all of them are false. The sky is blue. That one may or may not be true depending on where you live. If you looked outside and the sky was blue, then that would be a true statement. The moon is made of cheese. I'm pretty sure that's false. I'm also pretty sure that I'm not 90 feet tall, so that one's false. And you are a student, so that is true. All right, so there's some examples of statements. Now, not every sentence is a statement that we could use in logic. It isn't a statement to begin with. Okay, why is that? Because not all sentences communicate facts. All right, for example, go take out the trash. That is a command. That is not giving you any information. It's not communicating a fact. So that is not a statement. Okay, what about what time is it? Okay, so questions and commands are not statements. They're sentences, but they're not statements that we can say that they have a truth value, whether true or false. All right, now that we've got statements cleared up, we can start to talk about a way to organize all of this geometry information that you've already acquired and that you're going to continue to acquire. All right. Ideally, the best way that you could organize all of this geometry info in your brain is to think of it this way. Okay, so I have all of these geometry statements, all of these facts, okay, and some of them are connected to each other. They're all connected in some way to other statements. Let's get that straight. And we want to figure out as many of those connections as we can. Okay, let's clear up what I mean by a connection, and that gets into what I mean by reasoning and what I mean by inferring something. Okay, so let's start there. So as an example, suppose that I gave you on the next whiteboard the following. If you read in dim light you will strain your eyes. Okay, you read in dim light. Let's stop there. Okay, so both of these are statements, right? Now I'm going to show you how, and let's say that they're both true. Let's say that somebody told us, or we could assume that they're both true. All right. Now we're going to infer a new true statement. This is what I mean by that they're linked to each other. You can have statements that are linked. So it's true that if you read in a dim light, you'll strain your eyes. It's true that you read in a dim light. So therefore, the new statement that we can infer is that you strained your eyes. See that? Okay, so this is hugely important. So imagine that you had to memorize these three statements. Okay, now this is a trivial example, but can you see that if you memorize the first two, you would be able to infer the third one without memorizing it? Okay, so by using logic, we can decrease the amount of memorization of random, unrelated facts that we need to deal with. Okay, again, this is a trivial example, but there'll be other examples that aren't trivial, where there'll be lots of things we could infer, and what we infer at the end is not necessarily obvious. Okay. Okay, by the way, this is a good time to bring up some other terms. So when you have some assumptions, like I started out with 1 and 2, I said let's just assume that those are true. Let's assume if you read in a dim light, you'll strain your eyes, and then you read in a dim light. So those, you can call those assumptions. Okay, so we have assumption 1 and assumption 2. Now, when you are organizing a certain subject like geometry, you have a certain set of assumptions, and ideally you would try to infer all of that subject from a few assumptions. All right, and people have done this in geometry. In fact, the most famous person known for this was an ancient Greek mathematician named Euclid, and he had a few assumptions, and he derived books and books of geometry from these few assumptions. Now, when you do that, when you have a subject and you try to base everything on some set of assumptions, those assumptions are referred to by the fancy name axioms. Okay, those are the foundational assumptions. Okay, now when you infer new information, when you infer a new statement, okay, like here we inferred that you strained your eyes, that's called a theorem. Okay, so you want to infer theorems from axioms, okay, and then if you spell out the way that axiom, like here I didn't have to do a lot of work, but I was laying out what axioms infer this new statement, this theorem. Okay, this whole description, this whole presentation is referred to as a proof. Okay, I am now why do we call it that? I am proving, you can think of it as this whole presentation proved that you strained your eyes based on the axioms that we know to be true. Okay, proofs make theorems from axioms. Okay, so a lot of terminology here. Okay, what I'd like to do now is I'd like to give you some examples of proofs, and then I'm going to end this video, and hopefully the examples in the homework will further clear this up. We will not be doing, I'm not going to emphasize proofs in the homework for a couple of reasons. The SAT does not emphasize proofs. I don't know if you guys know that, but you don't need to do geometry proofs for the SAT. What I will do is I'm going to be going through proofs in the videos to help you to think about these geometry topics logically and systematically, to organize them in your brain. Okay, that's going to be our purpose for going through proofs. All right, so let's do lots of examples now, and some of them can be pretty fun to figure out how to infer from assumptions new information. So let me give you an example here. Okay, what about this one? So Victoria owns stock in companies alpha, beta, and gamma. So that's an assumption. If you like, you can call it an axiom. Okay, and then we've got some other assumptions or axioms. Yesterday, Victoria sold her shares of alpha, or so we don't know which one she sold, but she liquidated one or the other, alpha or gamma. Okay, this is if she sold. Somehow you also know this convoluted statement, but it's still a true fact. If she sold alpha, then she bought more shares of beta. Victoria did not buy more shares of beta. Okay, so can you infer which stock Victoria sold yesterday? Okay, so we've got a number of assumptions. We have 4 to be exact. And can we use reasoning? Can we use that information to infer a new statement, new true information? All right. So you might want to pause the video and work on this on your own. See if you can get it, and then I'll tell you what the answer is. Okay, so here is the way that I might play with it to get the answer. So the answer, she only owns 3 companies. We know that from assumption 1. So let me just refer to them by the abbreviation A, B, and G. Okay, so the answer has to be one of those 3. Okay. Now, yesterday the assumption 2 says that she sold either alpha or gamma. So that means that the answer is either, well, alpha or gamma. So we can eliminate B from the running. Okay, so it's only A or G. Okay, the first 2 assumptions got us that far. Let's look at assumption 3. If she sold alpha, then she bought more shares of beta. Okay, but the last assumption says that she didn't buy more shares of beta. So if assumption 4 is true, then she did not sell alpha, okay, because that would contradict with the last assumption. So therefore, the answer is that she bought gamma, okay. So that is the theorem. The theorem is that she bought gamma, okay. Now, a proof, I actually did the proof in words, verbally. I told you the way that I came to that conclusion. Okay, if you wanted to present a proof, and people sometimes, write out their proofs. That's usually what they mean when they say a proof, is they write things out. So if you spell out what I just said in words, like, okay, we know that it's either alpha, beta, or gamma. We know then it's either alpha or gamma. We know it can't be alpha. All of that presentation together, that makes the proof that gamma is the answer. Okay, gamma is the theorem that we sold gamma. The 4 sentences are the axioms or the assumptions, and then the whole explanation is the proof. See how that all works together? Okay, so that was a little bit more complicated proof. Now, of course, we can do proofs in geometry, not just with people buying and selling stocks. So why don't we talk about that now? What do we mean by, or let me show you an example of that. All right. Let's say that I had a, let's say that I had a line segment, and let's say that, let me put some names. To the endpoints. Let me make sure that, okay. So here we go. So I'm going to give you an assumption about these line segments, and then we're going to try to infer new information. So the first thing I'm going to assume is that AB is perpendicular to BC. We talked about what perpendicular means. Okay, and by the way, the compact way to write that is you use this symbol. It's like an upside down T. So AB is perpendicular to B. So that is our assumption. That is true. We're going to assume it's true. Now, can you prove, or is it true? Okay, prove that. Prove what? Prove that. Prove that angle ABC is a right angle. Okay, so that's going to be the new information we're trying to infer from our assumption. Okay, now this one I won't just say it verbally, I'll actually type it out. Okay, so you can see how you might deliver the goods. Okay, so you could say it, you can say it formally or in a kind of an informal matter. That doesn't is not so important as it is to get it correct. So you could say something like, being perpendicular by definition means that those line segments form right angles. So in other words, we know that they form right angles because that's the definition of what it means for two line segments to be perpendicular. Okay? Now, okay, well, there you have it. So therefore, oh, and then we also have to say angle ABC is the angle formed from these two segments. Let's get that clear. All right, and then therefore, angle ABC is a right angle. Okay, now how much detail do you need to list in your proof? Okay, that is subject to some debate. The safest thing, of course, is to put too much rather than too little. But you might have said, well, it's obvious that ABC is the angle formed from these two segments. All right. The safest thing is to not assume too much, because then it might not be clear that you know that you didn't just skip that. Okay, by spelling it out, it's clear that you know that that's true. Okay, so that's the safest thing. But in general, some people spell everything out, and some people cut a lot of corners. Okay, but here's one way that you could spell out that the fact that we know that ABC is a right angle, and so there is a proof that that is a right angle. Okay, using logic and reason. All right, inferring it from our assumptions. Okay, so far I have done what's called a direct proof, which means that I took assumptions, one or more, and I directly showed that the theorem was inferred from those assumptions. Okay, now there's a different kind of animal, and I want to close with that. It's something called an indirect proof. Okay, so let me, if in case I'm losing you, let me spell out first. Let me do some typing. Okay, so the one we've already seen examples of, direct proofs. These are proofs that directly spell out how assumptions imply a theorem. Okay, so that's all good and well and good. Now, indirect proofs do something a little bit different. Okay, these are proofs that show if the theorem was not true, that would lead to a contradiction. Okay, so again, probably the best way to explain this is with a couple of examples. I'll give you let me start with this one. So, all right, so imagine I was trying to show that, well, first let me put two line segments. And let's say that this first one had endpoints A and B, and then C and D. All right, and so here's the assumption. This is what you can take to the bank. The length of AB is not the same as the length of CD. All right. Now prove AB and CD are not the same length. Okay, so this is kind of a trivial one, but this is just to show you the what I mean. Okay, so let's see. Let's assume that A, B, and CD were the same length, and let's show that that makes a mess of things. Okay, so assume that AB is equal to CD. Okay, that means that AB does not equal CD is impossible. But we just said that had to be true. Okay, so therefore it's not possible that AB equals CD, because that would contradict our assumption. Okay, so therefore AB and CD are not the same length, because if they were the same length, it would lead to a contradiction. So they are not the same length. Okay, I hope that was instructive. Now sometimes the direct proof will be the way to go. Sometimes the indirect proof will be a lot nicer, easier for you, and sometimes you can do it either way. Okay, so let's do one proof. Let's finish with this. We'll do one proof both ways. All right, so let me make an angle here, and let's label the points C, D, E. Okay, and we can assume, or it's also sometimes called the givens, because it's given to you for free, you might say. Assume that the measure of the angle was not 90 degrees. Okay? And by the way, in degrees, when we talk about 90 degrees, we usually put a little, looks like a little exponent. That's a 0. That's the symbol for degrees. Okay? Prove that CD is not perpendicular to DE. Okay, so first I'm going to do a direct proof. Alright, so that we just directly spell it out. So here we go. Okay, well, if the angle does not have a measure of 90 degrees, then the line segments cannot form a right angle. Why? Because a right angle is 90 degrees. Okay, so I just spelled it out. So therefore the two line segments are not perpendicular. Okay, I just directly addressed why it had to be true that the line segments are not perpendicular. Okay, now let's do a indirect proof. Okay, and you're going to remember we assume that what we're trying to prove, we assume the opposite and show that leads to a contradiction. Okay, so assume that the two line segments are perpendicular. Okay, so now let's play with that. Okay, that would mean they form a right angle, right? And now we keep spelling out our reasoning. Okay, a right angle has a measure of 90 degrees. Okay, so what would that mean? That would mean that the measure of angle CDE would equal 90 degrees. Okay, and now the contradiction happens. But that would violate our assumption. So therefore, the two line segments must not be perpendicular. All right, there you have it. So the same theorem proved two different ways.